Hello, everybody, and welcome to this webinar. My name is Christian Tottrup, and I will be the speaker on this webinar. With me is also my colleague Natalie, who is supporting the logistics. Background-wise, I'm a senior project manager in DSI GRAS, but I'm also the project manager on the Earth Observation for Sustainable Development project, which is a large application project funded by the European Space Agency and focusing on satellite-based products and services in support of water resource management. So a lot of what you will be hearing today is the outcome of the activities that we have done within this project for the past 3 years. So I'm just gonna shift this off. Let me just review the agenda. The idea was first to give you a brief introduction on the relevance and motivation for using Earth observation for water resource management. Then we will go into specific use cases of applying Earth observation and thematically split between mapping and monitoring of surface water dynamics, Earth observation in support of natural disaster management, and also Earth observation as input to planning and management of water and agriculture. At the end, there will be a question and answers session. And altogether, I hope we can keep this within the 40 minutes allocated for the webinar. For questions, if you have them, as said, we will do it in the end, but you can file them in the QA button, which should be at the bottom or top of your screen. And then Natalie will review and collect them in the end, and we will go through them in the last session. So let me first introduce the project context and the context within which this webinar has been developed. So let me briefly play this short video giving you some background information to Earth observation for water resource management.
Water is easily one of our Earth's most valuable resources, but it is under pressure from overexploitation and pollution, and often affected by climate change. If our water is not managed carefully, it can lead to serious disasters. Water resource managers around the world require a solid information base to care for our water sustainably. They need to know how much water is available in a given area to ensure supply to all users. They need information about areas prone to flooding to protect the people who live there. And they also need to know about water quality to help avoid risks to human and environmental health. However, the information they need to make wise decisions is not always so easy to collect. Comprehensive water monitoring systems can be costly and easily destroyed. Not to mention, critical areas can be difficult to access. This is where the European Space Agency and its satellite Earth observation can bridge important information gaps, providing timely and objective monitoring of many components of the water cycle. A single satellite image has the potential to deliver reliable information on large areas. Using these images, models and tools can be developed to provide water managers with the data they need. For example, information on changes in a river basin's character, on vegetation cover and river runoff helps ensure a safe water supply. Earth observation can also provide critical information to prevent disasters caused by floods, droughts, landslides, or industrial pollution. ESA's Earth Observation for Sustainable Development Initiative works closely with international financing institutions and their client states to connect satellite information with needs on the ground, supporting sustainable development worldwide.
So that was the brief context, and in summary, the Earth Observation for Sustainable Development Initiative, as just presented, has a high-level objective of demonstrating the benefits of satellite-based environmental information for sustainable development. Now, the initiative is implemented with specific thematic focuses, and one being water resource management, where the project has worked with ongoing development projects in Africa, Asia, and Latin America to develop satellite technology applications, meeting user needs for making more informed decisions based on updated environmental information. The key motivator for the EO4SD initiative comes from the recent availability of the Sentinel missions. That is a new generation of satellite sensors from the Copernicus program of the European Commission. The Sentinel missions is delivered free and open data, and with an unprecedented spatial and temporal resolution, and with a guaranteed long-term continuity. Basically, it means that today we can do stuff with satellite images that we could not do just 4 or 5 years ago. So that's really a strong incentive to work with these data, and combined with existing long-time archives, these data can and should be put into practice to support water resource management. If we look in the context of water resource management, then there's a number of key priority areas or key EO applications where geo information is relevant and needed. For today's webinar, we will focus on using Earth observation for surface water dynamics monitoring, that is monitoring the extent, volume, and quality of inland water resources. We will be looking at support to management of water-related hazards like floods and droughts, and finally also how Earth observation can support agricultural mapping and monitoring, basically mapping and monitoring of crop areas and agricultural water use. Let's start with surface water dynamics. Throughout the world, inland waters is used for multiple purposes, including for irrigation, for livestock watering, and as a source for hydropower and recreation. And yet, in most countries, the official measurements of water resources is limited to major dams and river flow stations, which, however, is only representing a very small portion of the overall water resources. And this unmonitored proportion of water resources actually represent a major known unknown, which can produce inaccuracies and may lead to ineffective or erroneous decision making. With regular and systematic EO data acquisitions, it is possible to monitor, analyze, and communicate on the status and trends of all surface water resources, supporting national water resource management in respect to, for example, drought mitigation, irrigation management, and planning of infrastructure investments. Myanmar is one case where there's a lack of large-scale information about the country's water resources. Therefore, the EO4SD project has collaborated with the World Bank and the Asian Development Bank to improve the information base for water resource management in the Ayeyarwady Basin, which is the largest river in Myanmar, and also to improve irrigation in the central dry zone. In both cases, information on the inundation regime is needed for the proper infrastructure and flood management planning. So by using EO to map the seasonal, annual, and long-term frequency of inundation frequency, we can provide insight into dry and wet season water availability, and in a spatial detail where you can actually recognize individual fields. And hence, these maps can be used to pinpoint areas at risk for flooding and where interventions may be needed. And it's all information which is fed to national institutions who can use this information for more targeted planning and management. But EO can be used not only to track the change in surface water extent, but also the water level of water bodies can be measured. This is done by using satellite altimetry, which is basically a technique that determines the distance from the satellite to the target surface by measuring the travel time of a radar pulse. Traditionally, this technique has been restricted to larger inland water bodies only. Here you see an example from Lake Kariba, one of the largest reservoirs in the world, lying on the border between Zimbabwe and Zambia. And where you can see altimetry observations have been recorded over a long time period and showing the annual and long-term trend variations in water levels. Now, the interesting thing is with the new generation of satellites is the availability of many more suitable targets for water level observations, as shown in this map. In rough numbers, we estimate that plus 50 suitable locations for altimetry-based water level estimation is available within the Zambezi Basin, compared to maybe 5 or 10 targets with the older altimetry missions. Also, the accuracy of measurements is expected to become better with the new missions. And you can see in the figure on your right the comparison of water level as observed by the Sentinel-3 mission and compared to in situ water level observations at the river gorging stations in Zambia, and which are showing quite high accuracy and a high level of agreement. Those in time where we have seen a gradual decline in the in situ network, then satellite altimetry bears some important perspectives for complementing traditional in situ observations with space-based measurements of water levels. Surface water extent and water levels can be measured, but so can water quality, which is also something that is available through remote sensing data collection. And monitoring of water quality is essential in order to monitor environmental impacts caused by humans or by natural events. And yet, in many cases, in situ data collection network is inadequate for operational data collection on water quality. And here, the Earth observation can help, and it's widely recognized as being a reliable and cost-effective technique for describing and quantifying aspects of inland waters. Some of the relevant parameters is the chlorophyll concentrations, suspended sediment, and water surface temperature. Within the EO4SD project, we have worked with national authorities in Peru to provide water quality information for Lake Titicaca, which is needed for the evaluation of ongoing anthropogenic activities, and also for example, for identification of point source pollution and for better understanding of the eutrophication processes. Here you see a map of the chlorophyll concentrations. In principle, daily data can be provided, but because of cloud or sensitivity of clouds, then it's more realistic that weekly or 10-day information is being provided on the aspects of water quality. I would also like to highlight the relevance of monitoring surveys, water dynamics in the context of the Sustainable Development Goals. With the adaptation of the SDGs, as they also call, countries are required to measure and monitor on all the 17 goals and the 169 associated targets. And one of the indicators, which is very amenable to be monitored by Earth observation, is SDG 6.61 on the change in the extent of water-related ecosystems. And that is basically monitoring the change in open water and vegetated wetlands over time. So in an activity being supported by the Global Partnership for Sustainable Development data, partners on the EO4SD project have demonstrated how Sentinel data can be used to accurately map the extent of wetlands at a national scale in Uganda. And in addition to the mapping, a digital system was also developed and trained with the Ugandan authority, and allowing them for an independent mapping and reporting on the SDGs. Oh, sorry, wrong way. And here an example of the online reporting portal, which was then used to disseminate the results. As the next theme, we'd like to go over some aspect of how EO can support natural risk management. The motivation for looking into EO supporting natural risk is can very much be seen in the context of climate change, which is real and which will result in more frequent, severe, and less predictable floods and droughts events. The risk of natural disasters, therefore, a developing reality in many countries, and also providing a need for them to take appropriate measures to mitigate the impacts. And here Earth observation can support disaster risk management in many ways, from risk modeling and vulnerability analysis to early warning and damage assessment. If we look at droughts, then Earth observation-based drought monitoring is typically done using time series of Earth observation information on rainfall, soil moisture, and vegetation state, and comparing the current situation to the long-term historical situation for specific locations and time during the year. It's basically an anomaly detection. So looking at how does the current situation compare to the past situation. This was under the EO4SD developed in the Myanmar context, where a drought portal was developed, providing daily updates of relevant satellite data sources, and then their calculation into drought indices. Information which was made readily available in near real time to an online web interface, allowing users to identify the location, extent, and severity of droughts. And here illustrated as a trend in drought impacted area in the Magbai region during some severe droughts back in 2014. Satellite data can also be used to map and monitor floods, and then during the early months of 2019, we were looking at the flooding situation occurring in Mozambique and Malawi. I'd like to just play another small animation illustrating how radar imagery from the Sentinel-1 mission was used to map the extent of the flooding caused by Cyclone Ida along Beira in Mozambique. Flood maps which was shared with the African Risk Capacity, a UN agency working with the African Union member states to help better plan, prepare, and respond to disasters stemming from some weather-related natural hazards. Such maps are essentially for informing authorities and development organizations about the extent and impact from flooding events. And again, it can be used to target emergency response and development efforts. If we want to look at the impact for a specific disaster, in this case, we will again look at one of the really large flooding events and extremely damaging flooding events happening back in 2018, where Hurricane Nargis made landfall on in the Myanmar's Irrawaddy Delta, and with an estimated more than 80,000 people killed. The mortality, this huge number of deaths was blamed on insufficient warning. But we can also show that other factors were important, including large-scale agricultural expansion into natural habitats lying within a wave-exposed delta. By using historical data, we mapped the changes in mangroves over the past plus 20 years, and when overlaying this with a satellite-derived flood map, and also including detailed information about the land use in the delta, we could show that around half of the flooded area comprised reclaimed mangroves, mostly cleared since 1989. And at the expense of the clearance was at the expense of paddy fields. So if we look at in other parts of the world, it can be shown how mangroves actually can act as a buffer against tropical hurricanes. But as the mangroves were cleared in the Irrawaddy Delta, this buffering was lost, and the 3 to 4 meter high surge, which was generated by Hurricane Nargis, was easily flooding the largely unprotected paddies and people living along them. So some of the, we would say, the post-Nargis reconstruction efforts should consider this coastal agricultural expansion into the delta, looking at how to restore coastal wetlands so they can again act as a buffer against storm surges, and basically improving the resilience of the local communities against future similar events. As a final theme, we will be looking at water in agriculture. It is well known that water plays an essential role in the sustainable management of land, and in particular, when we talk about agriculture, with 70% of fresh water being used for irrigated agriculture. Earth observation can help in many ways by providing updated information on the extent of agricultural activities. It can be used to estimate the water evaporated by the soil and transpired by the vegetation, the evapotranspiration, which again can be used to calculate the water use efficiency. And altogether, that means Earth observation should have a role here to support better water resource planning and also management of irrigation. Under the EU4SD, we have tried to demonstrate this by showing how The Sentinel missions can be used to provide national crop monitoring information. Here in Niger region, and this is done on a seasonal basis and can then support, you could say, national or authorities in need to provide seasonal crop bulletins. But it's very much also done in the context of a new large irrigation development project being implemented in the region, and with the aim to extend irrigation activities and improve irrigation management in the region. And for such an activity, it's important to have a baseline in terms of how large an area is currently being irrigated, and against which you can then assess the potential impact or monitor the impact of the irrigation support activities. Earth observation is also important to support farm level irrigation. As mentioned, you can use Earth observation to estimate evapotranspiration, which is a key to understand agricultural water use. Basically, with ET, we can get information on the crop water productivity, the crop water deficit within large irrigation schemes, and helping to evaluate operators on when to irrigate, where to irrigate, and how much to irrigate. And the example here is from the Birni-Ankoni irrigation scheme in southern Nigeria. As a final example on how Earth observation may support agriculture and water management is the issue on water licensing. Here exemplified by Malawi, but in many of the sub-Saharan African countries have developed water licensing systems. But one of the critical issues in terms of effectuating the water license system is a lack of good spatial information about where the big water users are located. So in that sense, the mapping or national scale mapping of irrigated areas is highly relevant in order to compare the location of irrigation with the actual license registrations, and potentially then the identification of non-licensed water users. Actually, an implementation of Earth observation for such a purpose seems to have a significant scope for cost recovery. At least in Malawi, we estimate that about 75% the possibility for increasing the license fees with up to 75% if they had a better information base in terms of where agricultural water use is taking place. Which brings me to the summary and some of the takeaway messages that we have hoped to pass. First, there's a new generation of satellite sensors available, delivering free and open data with an unprecedented spatial and temporal resolutions and some long-term commitment. These data, combined with the long-term archives of already existing satellite images, has great potential to support sustainable development with critical information needed for decision making and planning, as well as for monitoring and evaluation. The Earth observation technology is especially useful in many developing countries where reliable water information can be scarce. We would, however, like to stress that we are not suggesting that Earth observation should replace in situ networks. Actually, the availability of in situ data is essential to calibrate and validate the retrieval algorithms. So it's more to see Earth observation as a complement to in situ data, offering cost-effective solutions for scaling up in both space and time. To ensure sustainability at the national level and uptake of the technology, there is a need to generate awareness and to develop and building capacity in using best practice methodologies and tools. So part of the EU4SD has also been about informing users about the potential of the technology, but also actually implementing capacity building in how to apply these tools. And for those who want to learn more about this, you could say do-it-yourself resources, then there's a number of sites here which could be a good starting point. There's many more available, but first of all, I can point you to the project website where you will find a lot of background information and also an online learning platform for Earth observation and support for water resource management. I would also like to highlight the Copernicus Research and User Support Service Portal, where you'll find webinars and tools to help users get started with exploiting the Sentinel data resources. The European Space Agency themselves has a number of education and training material also available at their home site. And then you have a number of other actors, and here I'm just going to mention the UN Spider Knowledge Portal, which provide information on how to use space-based technologies for disaster management and emergency response. So that leads me to the end. So before before finishing my talk here, I would like to acknowledge the contribution from our partners and colleagues working on the EU4SD project with the focus on water resource management. So thank you